Okay, welcome everyone at today's seminar of the Resurgent Asymptotics program. I would like to remind everyone that the lecture is recorded. So if you don't want to be seen or heard, please turn off your camera and microphone. If you would like to ask questions but don't want to be seen or heard, you can typeset your question into the chat and I will read it for you. So today's speaker is Professor Christopher J. Howls from the University of Southampton. Chris completed his PhD under the supervision of Sir Michael Berry in 1991 at the University of Bristol. Together with Professor Berry, they coined the term hyperasymptotics, which is a significant concept throughout this program. He was one of the organizers of a research program in exponential asymptotics at the Isaac Newton Institute in 1995. He's also one of the organizers of the current program. Chris held several lecturer and visiting scholar positions at various institutions before he arrived at the University of Southampton in 1999, where he is currently a professor of mathematics and director of the University Doctoral College. Chris is a leading expert in exponential asymptotics, hyperasymptotics, uniform asymptotics, catastrophe integrals, mathematical modeling, and applied mathematics in general. His talk today is about the higher order Stokes phenomenon. Without further ado, I would like to kindly ask Chris to start his lecture.
Okay, well, I'm blushing now. Okay, all right. Apologies if there is a bell ring in the background. I'm awaiting the delivery of 20 railway sleepers, and of course they would do it now. But anyway, okay. So today I'm being asked to talk about it's old work, but some work that has come up recently in the context of the theory of resurgence and whether this appears in the theory of resurgence or not. So the topic is going to be dealing with several things. It's going to be new Stokes lines, or rather old Stokes lines, but in a new context, virtual turning points that arise as a result of this, and then one explanation. There are other explanations, but one explanation of how this occurs, and that's the higher order Stokes phenomenon. So the collaborators on this, there are many. So there was myself and Phil Langman, my PhD student who now teaches at Charterhouse, Adri from Edinburgh, John and his student David Mortimer from Oxford, and John King, Richard Shue and Giles Bodie from Nottingham. And this was funded, work originally funded on an EPSERT grant. The papers that relate to this, what I'm talking about today, are all here. You can see the slides later, and there's the DOI's links to them if you want to follow that up. I should also mention that a significant amount of work, parallel work, has been going on in the Japanese school with a whole host of people based in around Kyoto and beyond. And there's a lot of body of work that they've carried out in this area using a slightly different approach, but nevertheless it comes to similar conclusions. And one particular paper, there's lots of papers, but one particular paper which you can look at, which has got lots of references in, is also listed on this page here. Okay, so let's talk about what was in the zoo before. So we all know about the Stokes phenomenon. That's the switching on of an additional asymptotic contribution, usually prefactored by an exponentially small term, as the Stokes lines, or if more generally Stokes surfaces, are crossed in some parameter space. So if I have a particular function y with a parameter a here, but the asymptotic parameter is k, so I've got a 1 over k type expansion. And then in the a space, I'm sitting in this particular point. There's this line here, which is going to turn out to be a Stokes line in a minute. And as I cross that Stokes line, what happens is that I acquire this extra term here. The Stokes lines are given by the imaginary part of the difference between the exponents of the prefactors vanishing. And in this particular case, this prefactor dominates this prefactor, so that condition holds down there. And we have here then these KNMs here are Stokes multipliers that then determine how much of this is switched on as you cross that particular surface. That's at the simplest, that's what the Stokes phenomenon is. More complicated things obviously are possible with infinite switchings on. This has been examined ad nauseam in the past using ARA examples, so that's all we really need to say about it. Basically, the Stokes phenomenon is a switching on of an asymptotic contribution. I've just spotted a spelling mistake there, that across the line. Stokes lines themselves emanate from turning points, or in higher dimensions, caustics of the problem, where the difference between these exponents vanishes identically, and more commonly the examples arise from adding this C in front of LG for the benefit of John King, treatment of second order ODEs. Stokes lines or surfaces typically run between turning points and go off to infinity. They repel each other. So in this particular example, this is say the simple harmonic oscillator. You've got essentially they repel each other. They don't cross each other, and they can also run, in the case of the upturn case, between turning points as well. The thing is that in this talk, pretty much all of what I just said on here can go out of the window, and that was what was discovered as a result of this work going some way back. And these are things which all of the reasons for these changes are the things that this talk will focus on. So the zoo now, we're going to be beginning to talk about the activity of Stokes lines here. So sometimes Stokes lines are there, sometimes they're not. That is different from the concepts of the relevance of a Stokes line, and I'll explain what I mean by that later on. The activity is, the relevance of a Stokes line really is to do with whether, even though the Stokes line is there, whether a particular contribution is contributing in order to switch on the subdominant one. The activity is, well, even though the contributions are there, nothing is actually switched on. And what we show how an exponential asymptotic approach, in fact a hyper one, going beyond the first exponentials, is important to understand the activity of the Stokes lines. Activity of Stokes lines that plays actually a significant role in, it turns out when you look at it, in integrals, ODEs, PDEs, linear and nonlinear, and it was relatively surprising that this had not come up before, given the amount of asymptotic work that had been going on, but you'll see in a minute the reason for that. And what this talk will do is it'll explain most of these things through the higher order Stokes phenomenon. So the idea of all of this went back to a paper in 1982 by Burke, Nevins and Roberts, and there they were considering a WKB approach to this third order equation given below. And what they were playing, the asymptotic parameter here is just x, and they were playing around in the complex x plane, as you do with WKB, and they noticed that in fact the Stokes lines themselves crossed. And then they also noticed that the monodromy of the solutions, in other words, going around and making sure you get to the same value in each of the sections, in each of the sectors delineated by the Stokes lines, they noticed that the monodromy didn't work unless they included new third Stokes lines at each particular crossing point. And just figuratively, this is what they had. This is essentially, when you look at this differential equation, you end up with a couple of turning points here in the complex x plane. And when they plotted the Stokes lines, rather than doing what happens in the simple harmonic oscillator and going up and repelling, in fact, they just went bang straight through each other. So this is something strange. They were using WKB approximations here, and obviously with these integrated phase components, it satisfies this cubic equation here. The solutions of these equations degenerate at these turning points; they become identical. And the Stokes lines in this case are given by this integral of the differences between the two, being the exponents of the asymptotic expansions. And what they found was that when they walked this side of this, what's called the Stokes crossing point here, and then they walked that side of the Stokes crossing point, then because of the relative dominance of all of these terms, it turned out that they didn't get the same answer. The only way they could resolve that was then spotting that actually what's not plotted on these curves, there are three possible solutions here, is there's this extra Stokes line that you have to include, and that Stokes line is essentially what's needed so that as you go around, you end up with the right monodromy. Okay, so just to point out that this was where 2 dominated 3, this is where 1 dominated 3, and this is where 1 dominated 2, the solutions of this equation. Okay, so what? Well, the interesting thing was that then it turned out that when they looked at the rest of the monodromy, it turned out that even though 1 dominated 3 on this side of the Stokes line, this side of the Stokes crossing point, this particular Stokes line didn't exist. So there's a rather strange thing happening here, is that first of all, you've got Stokes lines crossing. Secondly, you've got a Stokes line basically running from infinity and then stopping at what was an ordinary point. This isn't a turning point of any of these points. And thirdly, that then suddenly this Stokes line switches off on just the other side of an ordinary regular point. So that was what puzzled them. The other thing that they pointed out was, well, actually, if you look at the two different possible phases here, K1 and K3 actually coalesce when you hit the point in between. And this, therefore, should be, according to WKB folklore, this should be a turning point and things should blow up there. And what they actually found was that actually nothing bad happened there. And so this was termed a virtual turning point. They explained what was going on in terms of some complicated integral representations of that specific equation. But what we're going to show here is one way, a more systematic way in which you can explain it. But the too long don't read thing is that the activity and the changing activity of the Stokes lines is a general feature of asymptotic expansions that are arising from results of possessed Borel transforms, which involve 3 or more asymptotic contributions involving asymptotic parameters. It's not confined to the complex plane. We can provide an explanation based on the Borel plane, and we'll do that with an integral. But the reason this had not come up with for was pretty much simply because most of WKB focuses on second order differential equations for which modulo changing the lower point of the phase among the turning points, essentially there's only 3 or more independent, there's only 2, phase integral solutions from the differential equation. And you have to go to 3 to get to see this new effect. So let's explain this a little bit more systematically using our old friend, the Pearcey function. So the Pearcey function has 3 particular saddle points. It's got a quartic potential up there. It runs between some values at infinity, doesn't matter which ones. And what I'm going to do here is I'm going to have set the coefficient of the t-squared term x equal to 1, and we're going to look at this parameter a here and play around with that. So the saddle points of the Pearcey satisfy this cubic equation. There's no coincidence that I picked it. It's related to the original Burke, Nevinson, Roberts formula. So it satisfies a cubic equation. We have 3 potential contributions from the saddle points, and depending on which particular sector of the XA plane you're in, or in more general, the XA complex spaces you're in, different numbers of these different saddles, subsets of these saddles will contribute. They'll contribute with exponentially small prefactors and coefficients of terms like this, with a 1 on k to the r to the half contribution, except at the caustic, these red lines where they coalesce. So the saddle points can be written down, the contributions in terms of the saddle points and a and x there. Okay, so the subset changes as we cross the Stokes lines. In this particular, I've not drawn it very well. This is the caustics where they coalesce. The Stokes lines here actually come out evanescently above the sprout from that caustic point there, which is equivalent to the turning point. Okay, so what I now do in the whole next sequence of slides is I move to the point a equals 6/10 plus a complex number. Okay, so I'm going to 6/10 plus a half, and then I'm going to take a circular path around that particular point in the complex plane. And so this is essentially the real A plane, and then I'm going into the imaginary A plane here. On the right-hand side, I'm going to plot what it looks like in the original integration plane, the steepest paths. And then in the down below, I'm going to plot here what's in the Borel plane, which is essentially where the singularities, the exponents of the 3 contributions line up. And then the A1 through the A9s are going to be the particular points that I'm going to look at and focus on. So let's start at A1. And if you look at A1, then if you go to the original integration plane, you have a saddle point at 0, you have a saddle point at 1 and a saddle point at 2, but the steepest path just runs from here and goes up to here without encountering 1 or 2. Okay, so at that point, there's only 1 contribution. As I move to this particular point, A2, which lies on here, this point here, this line here, which I'll explain in a minute, what happens is I get a Stokes phenomenon, because the line, the steepest path from 0 connects with 1 and then shoots off to its valley. So I pick up another contribution, and you can see that at this point, the F1 aligns horizontally with the F0, and that's characteristic of the Stokes phenomenon. So this is the Stokes line for basically 1, 0, and 1, with 0 dominating 1 at that point. The saddles connect, and you can see that the integration contour here, the collapsed integration contour in the Borel plane, F1 snags on it and would then generate an additional contribution. Okay, so now I move to A3 and I get the full contribution from 1, and then I go to A4 and I just get a contribution from 0 and 1 and nothing happens. Then I go to 5, and at 5 what happens is I now get the connectivity between 1 and 2. I've got 1 and 2 lining up and 1 dominating 2, and so I've got a Stokes phenomenon going on between 1 and 2. And as I then move on, when I'm in A6, then essentially I've now got 3 contributions. Sorry, that should shoot up here and come back. That I got 3 full contributions from the critical points, the saddle points. As I move to 7, what happens is, I think this has got out of sync, sorry. As I move to 7, 1 now reconnects, oh, sorry, it swings back here, and I get 0 and 1 about now to disconnect, okay? And again, that turns out to be a Stokes phenomenon, because at that point, I lose the contribution from 1. When I get back to point A8, then essentially I can see that 0 and 2 are about to disconnect. And so when I go back to A9, essentially I'm back here and I've only got 0 connecting there. So you can see that I've got 3 Stokes lines. I've got this Stokes line, this Stokes line, this Stokes line, and this Stokes line. And immediately you can see that something strange is happening, which we'll explain in the next few slides. On this particular Stokes line here, you'd think that this Stokes line should continue through here, because this is between where 1 and 2 are connecting up. The reason that this line isn't here is because this is actually irrelevant, in the sense that it would only be a Stokes line if contribution from saddle point 1 was actually present, and then it will be the contribution from saddle point 2 will be snagging on the integration contour in the Borel plane from there. Well, actually, the saddle point 1 is no longer contributing, so it really doesn't matter what's happening between 1 and 2. It's irrelevant to the actual particular function that we're interested in. So although that particular Stokes line is irrelevant from the point of view of the function we're looking at. So that explains why that one doesn't continue beyond this crossing point. But the next thing is that when we want to look at this Stokes crossing point here, at this Stokes crossing point, what you see is that all of the 3 line up in a particular row. Why? Well, because I've got 2 lining up along this Stokes line and the other 2 lining up along that Stokes line. And so, and with this constraint here, they all then are basically, you've got a double Stokes phenomenon going on at that particular point. So that's a regular point. Nothing nasty is happening in the terms of the asymptotics from that, from the asymptotic expansion terms, but nevertheless, the 3 have lined up. So that is the Stokes line here between 0 and 2. But on this side, we see that actually this particular Stokes line doesn't exist. If you look at what was happening at that point A4, 0 and 2 were lining up, certainly, but there didn't seem to be any change. If I look at the top, if you think back to what the integration consoles look like in the original plane, there wasn't anything going on between 0 and 2, no connectivity going on there. So that looks like a bit of a strange thing that's happening. And so that the Stokes line suddenly stops at this particular regular point. So that's what we need to explain. And the higher order Stokes phenomenon is how I'm going to explain it. There are other alternatives available, but this is how I'm going to explain it. Let's look at what happens at this point A1. This point A1 was chosen for a particular reason. Now, what I've drawn in here in this blue line is what eventually is going to, I'm going to explain what it is, but this is actually what's called a higher order Stokes line. It goes between turning points. These are actually turning points here, and it runs through this Stokes connection point. At that particular point, you find out at A1 that all of these singularities in the Borel plane line up. They are collinear, okay? Not necessarily horizontally, but at some radial going out from the most dominant one, F0, they are collinear. If you look in the actual original integration plane, then nothing actually special is happening. 0 isn't connected with 2, it's not connected with 1, so it's just an ordinary boring Stokes line that's happening. It's an ordinary boring contour of integration there that's happening. So that's rather strange, and that's another indication as to why this wasn't even spotted in integrals before, because if you just look at the original integration domain, you wouldn't think that anything strange was happening as you cross this particular point. But actually then what is happening? Well, at an ordinary Stokes phenomenon, we know an exponentially small contribution is switched on or off across this particular Stokes curve. Whereas on a higher order Stokes phenomenon, the possibility of a Stokes phenomenon is switched on or off. So what does that mean? Well, the effective Stokes multiplier is changing, and what's really happening is the more distant Borel plane singularity is dropping off onto a different Riemann sheet. And that blue line that I drew is given by these set of parameters. A satisfies this condition, that 0 to 1 divided by 1 to 2 has to be real and positive. And that's a condition for collinearity in the Borel plane. So what's happening? Well, before, if you like, the higher order Stokes line, you can have, say, 0, 1, and 2 here. And 0, if you look out, you can certainly see 1. But in order to see 2, it would have to walk around 1 and then drop onto a different Riemann sheet. As they line up and become collinear here, they're all along the same line, the same cut, if you like. And then as you go beyond the higher order Stokes line, then what happens is, well, 0 can still see 1, but now this 2 line here has popped up back beyond the cut that's coming from 1, and it's popped back onto the sheet, and then it's directly visible from 0. So essentially at that point, you can think of the effective Stokes multiplier in the higher order, the strength of the Stokes multiplier has gone from 0 to something that non-zero. Note that there's no change in the form of the ordinary asymptotics. As we'll see in a minute, there's a change in the form of the remainder terms, but in terms of the ordinary asymptotics, nothing has happened. You can confirm that things are popping onto different Riemann sheets by looking at the Borel-Pardais approximation to what's going on. So what does that mean? Well, if I have an asymptotic expansion here and I divide by the appropriate factorial, this is basically a Borel transform of what was a divergent sum, eventually divergent sum, and I can turn it into a convergent integral. Now that by itself is okay, but what I'm interested in doing here is I'm interested in now taking this Borel transform and taking the Pardais, the NM Pardais approximate for that. So that's basically doing polynomial representations in T, where T is the Borel transform parameter top and bottom, up to the usual Pardais linear terms. And then just to illustrate it, then just to make the point then, of course, that this Pardais approximate here, if I then do the Laplace transform of this gets me back to the Borel-Pardais resummation of what's going on. So that would give you, in theory, the exact, or numerically exact as far as how you wanted to go, representation. So let's do this for the PSE. So here are the coefficients of PSE in terms of Gegenbauer polynomials. I can look at, I'll look at it, say, around the particular critical point 3 here, and I take this sum. I can take up to 200 terms here, and then I can look for the almost off, the slightly off diagonal element, 100, 101, which seems to work best. And I'll be sitting at this point A1 and looking around that point. And if I do that, then just to show you, you can do it. It's gorily horrible, but you can do it. This is the Pardais approximate you can get for the 101, 100 over 101. And then what we're going to do is we're going to look at the poles associated with that Pardais approximate, because that will give us an indication roughly of those will be approximating the cuts of where they're coming from, the critical points. So here we are. So let's start off on this Stokes line here. The red dots in this diagram are going to be the Borel planes, and so these are where I've called them the singulant. So this is F0. I've shifted everything back to 0 so that F0 is at 0 effectively, and then everything is shifted by that amount. So these are the singulants here. So the red dots are the actual positions of the singularities at this particular point here. And you can see that then obviously the poles here are trying to, and we heard about how the poles try and coalesce and give the they attract with each other and then give the cuts. So at this point, you can see that 0 and 0 dominates 2 because 2 is off to the right, and it will see it because essentially there's nothing to stop it seeing it at this point. And you can see that the Stokes line is active and it will switch on that 2 as it crosses it. As you move to here, you can see that the singulants have moved around. Here, this is where 1 sees 2. 2 has been switched on, remember, but 1 has not been. So essentially, the fact that there's a potential Stokes phenomenon going between 1 and 2 is irrelevant because 1 isn't there to switch on 2. So that's an irrelevant Stokes line. If we then move up towards the higher order Stokes line, you can see things are bending around. And you can see that exactly when we're on this higher order Stokes line, you can see that everything goes collinear. So essentially, this is effectively saying there's a cut coming from here and a cut coming from there. And then what happens is, as we go beyond that, you can see something magical happen to these poles. Beyond that, you can see that actually there are no more poles hanging. I've had to draw that red dot in. After that, the Parde approximant knows nothing about that particular singularity. It does know about 1. And so the point is, what's happened here is that 2 has dropped off onto a different Riemann sheet, because 0 can only see the Parde approximant, which is centered on t equals 0, only sees these singularities. It sees no singularities arising from 2. So that confirms essentially that saddle point 2 has dropped onto a different Riemann sheet. And moreover, of course, as you go around, then you can see, not surprisingly, when you get back to this Stokes line on this side, as you know from the asymptotics, nothing is happening. And that's consistent with this Parde, because again, the only singularities that can be seen from the t equals 0 is this f01. And even though f02 is lining itself up to try and have a Stokes line, it's not. It's on a different Riemann sheet. It doesn't see it. It's not there. Okay, so the Stokes lines basically all end at that regular turning point. So that is essentially confirming what happens is that at the higher order Stokes phenomenon, the singularity generating the dominant contribution drops onto a different Riemann sheet. A feature of the higher order Stokes lines is that if you think about Stokes lines are given by, they involve this asymptotic parameter here, k, as well as this parameter space, the exponents here. And so if you vary k from being real to complex, then you can sort of shift the Stokes lines around. So this is k real. If I shift k to be a complex value, then these Stokes lines will shift around here. And the Stokes crossing point moves around. It will move around on this higher order Stokes curve as it does that. But the higher order Stokes curve is irrelevant. Sorry, k is irrelevant to the higher order Stokes curve. It doesn't depend on that. There's no k in this definition for collinearity in the Borel plane, and therefore the higher order Stokes constant is an invariant of the asymptotic parameter. It's just definitely there. It's a function of these exponents at that point. So you might say, well, how often does it occur? Well, a Stokes line basically occurs when 2 exponents line up horizontally in the Borel plane, 2 or more of them. So this is essentially that you've got a 1 constraint here, that the imaginary part of the difference between the 2 has to be equal to 0. For a higher order Stokes line, you've got to have 3 things lining up, which looks like an extra constraint. But the key thing is they can line up in any direction. So that removes one of those constraints effectively. And so essentially there's only just 1 constraint. So they will occur just as frequently as just 2 lining up along a particular direction. 3 can line up along any direction. So effectively they're just as common in some sense. So whenever higher order Stokes phenomenon can occur, not always occur, but they can occur whenever 3 or more different non-repeating asymptotic contributions in the independent Borel plane exist. That means that they will occur for things like inhomogeneous second order linear ODEs, which of course you can differentiate to get a third order homogeneous ODE. For higher order, any higher order linear homogeneous ODEs, second order nonlinear ODEs, single, multiple, or integrals, and PDEs quite commonly, as we'll see in a minute. So pretty much they occur everywhere except for the second order ODEs, which was the focus of a lot of WKB theory in the early 20th century. So all of this is fun, but does it actually have any effect at the end of the day? Well, let's do an example and to try and show you that it might do. I'm going to do 2 examples, one a linear PDE and one a nonlinear PDE if I get time. And this original example was John Chapman and David Mortimer's idea. And they attacked this problem using matched asymptotics and derived pretty much similar the same answers as we end up with. But myself, Phil Langman and Adri looked at this from the point of view, we cheated, as you'll see in a minute, and we looked at it from the point of view of an integral representation, although that you can actually do all of our analysis using just looking at the coefficients of themselves as well. But the point is that it's basically a third order PDE system. Epsilon, I'm switching from large K to the applied mass small epsilon parameter now. It's an inhomogeneous PDE with a time dependence here. We're going to look at it over full X and T positive. The initial data is constructed as arctan of X, and will require the bounded derivatives as mod X goes to infinity. So dominant balances, you can do that, and you can show that, of course, the leading order behavior is arctan of X. So there's no T dependence or at leading order, but that will come later. And if you look at the other balance that's there, you've just balanced these two off, you see that you can get some oscillatory solutions. That doesn't satisfy the initial condition, and so therefore it doesn't look like this should appear anywhere in the solution. Okay, as we'll see later, things of this type really do, and they are important for the late time behavior of what's going on. So there's another example here, is that don't just assume that what happens at t near to t equals 0 is what's going to happen at t goes to infinity. This actually turns out to be subdominant, these contributions. So don't even just worry about just your leading order subdominant behavior. Sometimes you have to go further. So the way that Adri, Phil, and I cheated was that we looked at this from the point of view of Fourier integrals. Essentially, the solution to this differential equation can be written as the sum of 4 integrals. Essentially, there's 2 independent ones and then 2 complex conjugate ones here. I1 is got some saddle points, and it's got 2 saddle points and 2 poles, and I3 has got basically no saddle points, just an endpoint and some poles. Obviously, I1 has got some endpoints as well. So all of this can be explained in terms of endpoint, saddle points, and pole asymptotics. However, you can go through, I have a separate talk where you can go through and do it in gory detail using the coefficients as well. So we'll base everything on this leading order approach here. And the types of different different contributions that can feature in the expansion are the following. So looking at the integrals, it's not too difficult to see that you get an endpoint contribution. This always contributes, and it has something of this form with this epsilon expansion. So that it's essentially an e to the 0 here. So the Borel plane singularity is going to be 0 here at 0, and that power series expansion. You're going to have a saddle point, which has saddle points which have these expansions. There are 2 saddle points. Only one of them is going to be relevant, and then the pole contribution turns out to be here. And this is the subdominant contribution, which actually becomes more important as t gets bigger, or it plays a role as t gets bigger. So there's an interplay between these as to which ones are contributing. And so then if you look at the Stokes geometry, what do you have? Let's start off, this is in the xt plane. And then in this sort of little triangular wedge down here near to t equals 0, if you look at the contributions from the integrals, essentially you only get one endpoint contribution. There's a pole and a saddle. There's another pole symmetrically over here and a saddle point symmetrically over there. But since you're running from 0 to infinity, the only thing that counts then is this particular endpoint contribution. Okay, so then as I cross this line here, which is a Stokes line, you can see that what happens is that the endpoint snags then on the saddle, and you get an endpoint plus saddle everywhere in this sector here. And then as I cross this Stokes line, this is a Stokes line between the saddle and the pole, and you can see that what happens is the pole and the saddle sweeps through the pole, picks up this other contribution here, and you get a pole contribution. So in this sector here, you get an endpoint, a pole, and a saddle point. So now let's move around the other way. If we move around the other way, you go from across this line here, which is an endpoint pole, a Stokes line. This is the real t-axis, and you can see that what happens here is that as this steepest path sweeps around, it snags on the pole and picks up an endpoint in the pole. This particular line here would be a Stokes continuation of this Stokes line here, which would be where the saddles would want to switch on, play around with the pole, but the saddle point isn't there at this, it's not contributing, and therefore this is irrelevant. So this endpoint and pole continues all the way up until you hit this line. When you hit this line, this is again where the endpoint and the saddle is a continuation of that line. The endpoint and the saddle snag on each other, and you go from just the endpoint and the pole to the endpoint, the saddle, and the pole contribution here. So you get EPS. Now, if you look at the extension of this line as you go across here, this would be where the endpoint and the pole play around. Well, I've got the endpoint and the pole playing here. So you would expect that something should happen. As I go across here, I've got endpoint, pole, and saddle. And so you should expect perhaps that the endpoint and the pole should switch off. Well, in fact, it doesn't. As you can see, if you just analytically continue around here, you can see that it's on the wrong side of the pole to be able to do that. And so the endpoint, the endpoint just moves, and it just moves, and nothing particularly happens. So essentially, you've got this particular Stokes line here, which should be a Stokes line, isn't there. And so you don't get it going to E plus S, which will give you a contradiction. This Stokes line here is actually not there. It's inactive, even though it was active here. At this particular point A, nothing particularly bad occurs. This is just a Stokes crossing point, and this is where all these lines, these the Borel plane singularities, would line up and be collinear. So if you then look at the singulants, these are the singulants you can write down that are all relevant in terms of the Stokes lines and coalescences and things of this type. And the two ones that are important here are the ES1, the endpoint and the saddle, and the saddle point and the pole. It's the ratio of these two, which then when you put together and make that greater than or equal to 0, defines this particular line, which is the higher order Stokes line between the endpoint and the pole. That is the thing, the mechanisms we've seen from before, is the mechanism that switches off this particular Stokes, the activity of this Stokes line here. And so what's effectively happening is, as you cross here, is that the endpoint, the equivalent endpoint, the image of the endpoint in the Borel plane, the pole is dropping onto a different Riemann sheet as you go across there. So the Stokes phenomenon, we can see you actually switch on and off terms, and the number of terms in the asymptotics contribute. But in the higher order Stokes phenomenon, you change these Stokes constants. Effectively, the Stokes constant of the pole, in that case, became 0 at that point, the magnitude of the Stokes constant. It changes the number of remainder terms, I'll show you in a minute, and so it changes the potential for the Stokes phenomenon. Now, why do I say the change in the potential? Well, if you think back to hyperasymptotics, if you remember the first lectures, essentially what happens when you iterate the re-expansion of the remainder of an asymptotic expansion, you generate, this is your original asymptotic expansion, and here you can generate the first correction terms, and these are the Dingle terminants. And then when you iterate again, you can generate some other terms involving other remainder terms, other Stokes constants involving higher order integral generalizations of the Dingle terminants. That's just a simple case. Obviously, you can have nonlinear and log versions of these as well. But in the simplest case, that's what happens. So if we go back and look at that in the terms of the endpoint contributions that we've got, these are the endpoint contributions. And if you do the analysis, what you find is you get the endpoint expansion is this. This is the asymptotic expansion associated with the endpoint. But you can then write down the exact remainder. And the exact remainder turns out to be the sum over the two adjacent saddles. So both saddles contribute to the remainder term, not to the overall expansion at the leading order. And you have two poles, and you get two contributions due to the poles. And this is a nice, simple, the way in which it works out, this is just a simple incomplete gamma function here at this point, because the pole contributions just terminate. The saddle point contributions would take this form. So this is the expansion around the saddle point, but these are its remainder terms, again, in terms of around the poles, plus this term in terms of the remainder about the other saddle point. We'll focus on saddle point S1, which is the one that's important for the endpoint contributions that are going on here. What then happens is that as you go in, this particular integral here would switch on as FEP varied, the singulant between the endpoint and the pole varied. This would switch on the pole contribution at the Stokes phenomenon. What we can then do is we can take the integral saddle point contribution, we can take it in here, and up to a change of variables, you just stick it into this remainder term here for its hyperasymptotic re-expansion, and this is what you get. The endpoint expansion then is whatever we had before. It's got its endpoint contribution, and now we only focus on pole 1. It's got this contribution here, and then the contribution going from the endpoint to saddle point 1 to pole 1 basically is of this form. It's this double integral, a v integral and u integral. It's got some mess here, which isn't so important. But the key thing is that you can see is that you then acquire this term, which has a pole where, again, this is a condition for collinearity in the Borel plane. And this translates to the presence of a pole here in this this second order remainder term in the hyperasymptotic expansion. And this is the key thing from an algebraic point of view as to what is then happening. The residue of this particular double integral, when this particular collinearity occurs, is exactly the contribution from pole 1, the remainder term from pole 1. And so there's an exact cancellation between the residue here and this particular term here. And so before the higher order Stokes line, you have this integral this representation for TE in the hyperexpansion. After it, you lose completely and exactly the contribution from pole 1. Since that contribution has vanished, there is no possibility of any pole contribution from this denominator here switching on across the Stokes line. And at that point, it's gone, it's vanished. So the role of the higher order Stokes line is basically to kill off this term so that actually you can never have a pole, you switch off the Stokes line and you can't have that pole, endpoint pole Stokes phenomenon for t greater than the Stokes crossing point. If you look at the things numerically, what happens is, this is the exact numerical computation for epsilon equals 0.5 for that PDE solution going forward in time. If you then plot the asymptotics for that, neglecting that initial sub-dominant term, so this is more of a point about neglecting sub-dominant terms, this is what you get. So if you go back, you can see that there's a little bit of a fine structure here, which you lose when you include that sub-dominant term. But when you plug that sub-dominant term in, you see that you do recover that fine structure. So essentially, this is obviously a smaller wave than over here, but essentially this if you want to capture that fine structure, you do need to include that higher sub-dominant term, which comes about taking account of the higher order Stokes phenomenon as well. So if I take a time slice through that at t equals 30, this is the exact solution numerically found, and it oscillates a lot. If you don't include do any of the hyper and you just do the simple asymptotics, you get something that looks nothing like the exact result. If you do include hyper, you do begin to, and the higher order Stokes phenomenon, you do begin to recover it. This particular thing is an unavoidable caustic that is a nasty thing you can't get rid of, but it's there. So you have to do a uniform approximation at that point. But if you do just to compare this and this, if you put it together, you can see that clearly this is a much better approximation, except in that region, than this one was there. And so that's an illustrative example of how the higher order Stokes phenomenon is important, and including sub-dominant terms as well. So this is then the general structure that you have for a higher order Stokes phenomenon, what this effect is on an asymptotic expansion. It doesn't affect the dominant asymptotic expansion, but if you're looking in the re-expanded remainder terms or the remainder terms themselves, then it will do that. So this particular tree structure that you have in a general hyperasymptotic expansion, you have the first term, then it branches off into adding all these other terms in, and then each of these branches off into their re-expansions. What happens is essentially a higher order twig, if you like, of one of the branches of these hyperasymptotic expansions. What happens is a pole, there's collinearity of the singularities along in this particular singular, or in this particular hyperterminant here, which the pole of this gives, the residue at that pole gives rise to something that actually kills off an entire other branch. So this is sort of like almost like a butterfly flapping its wings. A little butterfly flapping its wings on this twig here basically causes this whole branch at a higher order level and its subsequent branch twigs here to fall off. And so it shows quite a powerful effect of the higher order Stokes phenomenon on results. And if that can be interpreted as the Stokes multiplier K effect in this branch here, changing to become 0, it's equivalent to the singularities dropping on to the different Riemann sheet. So in the last thing I want to talk about are virtual turning points and how this relates to that. So the higher order Stokes also explains the activity of virtual turning points. You can probably guess how already, but let's just run through an example. The inactive portions of Stokes lines can lead to virtual turning points. If you remember, a turning point is where two or more exponents coalesce. So in terms of the singulant, it's where that goes to 0. And if you look at the leading singularities in the expansion coefficients, you can see the signature of that is because if they depend on that singulant, like a factorial over power, clearly if that goes to 0, the actual terms in the expansion are going to blow up. So that's usual signature of a caustic or a turning point. But at a virtual turning point, essentially, the key thing in a virtual turning point is this Stokes constant here has effectively now become 0, or it's changed from what it was before the higher order Stokes line to 0 after it. And so no singularities in the expansion. There's no contribution from that particular singulant that's going to 0 here. And so the K and M has switched it off. And so that contribution is gone. And so there's no divergence of any of the particular terms in the expansions. So an example of this is Berger's equation. So this is, again, done with John, Adri, and myself. And so Berger's equation, why pick it? Well, this is, again, the cheating thing because we can solve it exactly, but you have to have baby steps before you can actually go on and do more complicated problems. But we'll look at Berger's equation here. Epsilon, again, is small. We can make it complex if we want. And we're going to look at this 1 over 1 plus x squared hump for the initial data. Now, we can easily solve it using Cole-Hopf exactly, and with integral representations here, with f taking this form and g taking that form. We can do it that way. Actually, we solved it both ways. But if we look at it, we can look at it using just ray analysis. So if you look at this, the rays of the PDE are of this type. X is S plus U of S naught and T. So S is, if you like, the parameter along X, or determining which ray you're on here. And if you plot those rays, you can see that the rays go from the initial data, and they have slopes given by U of S naught. And you can see that eventually they're going to cross. And at certain points, they have caustics here, where they're tangential, and the caustics, of course, are given by here, where they form an envelope of the rays. Inside, you've got 3 real rays. Oh, look, that's looking a bit Pearcey-like as well. And you're outside, you've got 1 real ray and 2 complex rays here. Okay, so of course, we know that Berger's, what happens is that what starts off as a nice 1 over 1 plus x squared, eventually it moves to the right, and eventually it forms a shock. And it's not because of the epsilon being positive, it's not an abrupt shock, it's a smooth shock. And so, but nevertheless, you get this smooth shock behavior, and this is how the shock wave forms. From Cole-Hopf or from playing around, you can see that essentially we can work out the location of the shock. The leading order behavior is given by a ratio of these two expressions here. Broadly, you've got an F1 and F2, an A1 and A2, and that are related in this way, with a B1 and a B2 on the bottom. And then if you look at what's happening is that upstream of the shock, then essentially where F1 is less than F2, you get the shock is U of XT is effectively A1 over B1. And then downstream of that's downstream of the shock, then upstream of the shock, this behaves where F1 is greater than F2, and A2 over B2 is the dominant behavior. And then actually when F1 equals F2, that is effectively the location of the shock wave, and that's the smooth shock location, and that's where you get the most rapid change. And there are energy balances you can look and Maxwell type things you can get to justify that as well. Okay, so let's now look at this now from a trans-series approach rather than doing Cole-Hopf and see what happens. So we're going to first of all look from a solution of this type. We're going to look for a simple epsilon power series expansion around e to the 0. Why is that e to the 0? Well, if you look at the ratio here, depending on where you are upstream or downstream, essentially you've got an e to the 0 type behavior. So the trans series will be an e to the 0 to start off with. If you substitute that into Berger's, of course, since it's nonlinear, you will get your trans series, and you'll get the full asymptotics, formal asymptotics of this form. There's a coefficient c to the n, a sub n, where the a sub n are the n times the f of x, t over epsilon, the WKB type solutions here. What do these f satisfy? These f satisfy this particular nonlinear first order differential equation PDE, sorry, here. And the key thing is, and this is the beauty, unlike when you solve PDEs numerically, you want to stay away from caustics. Actually, caustics here are the absolute structure on which everything is, the bones, to quote another context, the bones on which you sew the flesh, of which where the FJs vanish on the CJs here, J equals 1 and 2. And you can see that the real caustics, if you plot everything in the imaginary X, real X, and real T plane projection, you've got, here's the real caustics. Here they meet at this caustic point here, coalescence point, and then they go off into the complex plane up to the singularities of the initial data, plus or minus I there. And on those points, this is how you can, these are the boundary conditions that you play in that allow you to solve this equation and get the exponents correctly. So then you use Sharpie to solve for the Fs, and you can play around with the boundary data, and you can then spot that you can get 3 solutions, and there's one which is 0, and then there's 2 other ones, which I'm going to call 0, 1, and 2. And essentially, because you've now got 3, you can then think about having a higher order Stokes curve, because this is where the ratios, the 1s and 2 of them, they're all collinear in the Borel plane. The Fs are collinear in the Borel plane. So what if I do, so what I've done here is essentially, this is the complex X plane, where I've taken a slice through a constant value of T. And I'm going to walk from this side of the shock through the caustic to hit the shock and then go back onto the other side. And so there are some Stokes lines you can plot here. 0, this green one is where 0 dominates 1. This light blue one is where 0 dominates 2. This dotted one we'll see is going to be an irrelevant one. And then we've got where 0 dominating 1 going here. This CR is the caustic between 0 and 1, which we'll have to deal with in a special way, but we'll carry on with that. So if you put the boundary data in, it's quite easy to show that F1 and F2 are not there on the right-hand side as X goes to infinity. So we're pretty sure that the trans-series solution takes this particular form A0. And it turns out actually that because F1 and F2 can't be there, then it turns out that this C is actually 0. So this Stokes constant, this trans-series, right on the real axis, on the real x-axis to the right of that particular caustic, turns out to be just the leading order boring power series and epsilon solution here. Now, as we walk towards this caustic, so we sit here and we walk towards this caustic, we can't really do anything. That there is a genuine blow up in this non-uniform expansion at this particular point. We'll talk about that later on. So what we do is we decide that actually what we're going to do is we're going to walk around in the complex plane to try and get towards this shock point, which is this red point here in the complex X plane. So if we look in the Borel plane here, what have we got? I'll have to speed up a bit. Here is the original Borel, if we were solving this as a Borel transform, here is 0, and this will be the integration contour that we would do to integrate the Borel transform. The green bits down here corresponds to the multiples of repeat F1 and its multiple repeats. The white bits are the F2 singularity and its multiple repeats as well. And so as we walk around, we start off with nothing, with only the boring epsilon power series at this point on this line here. As we hit that Stokes line, you can see that the green lines, the ones, all line up and will snag on the integration contour from 0. So we will pick up we will pick up additional contributions given by C on this line, half K1 here, whatever the strength of K1 is. And the ANs then are these trans-series contributions of this type. As we walk further on, you can see now we've picked up all of these infinite number of contributions. So because C is 0, we've now got C wasn't there. I just put that in to show the form a bit. Here you've got K1 to the n times all of these. So whatever the original K1 is, the nth power repeats with all the other ones. And as we walk further on, when we get to this Stokes line at 2, well, this would be a Stokes line, except that 2 isn't there. It's not contributing. So even though there's a snagging between 2 and 1, 2 isn't contributing at that point. So it can't actually, it's not there to switch on 1. So that's an irrelevant Stokes line. As we move then further on to the higher order Stokes line, you've got basically everything lining up. So you've got a doubly infinite set of singularities lining up along this ray coming out from 0. So this is where we think things are going to happen. And it's not surprising to see that actually all the ones are going to move on to the cuts through the cuts on coming from the 2s. and onto the different Riemann sheets. And they'll all be on mutually different Riemann sheets. Essentially, there's no change in the asymptotics going on here. So as we walk around here, these are green contributions. They're still from 1, but they're now on a lower Riemann sheet. Nevertheless, they still contribute to the overall sum. They drag with them the contour that they had before, and they're still contributing. So we have an infinite number of contributions. It's just that infinity minus one of them is actually on a different Riemann sheet. Then we move back to the real line, and everything lines up again. Okay, so everything is now on this would be a Stokes line of 0 dominating the 1s, and that could be a Stokes line happening, except remember that all the 1s are now on different Riemann sheets, so this isn't going to actually cause a Stokes phenomenon. And then as we move along, as we move towards the shock point, everything green, everything moves basically towards 0, and all the 2s move to 0, and so actually everything coalesces at that point. Okay, so at that point we should expect a super divergence, because you've got an infinite number of singulants all going to 0 at that particular point, but nothing actually happens. That's actually the position of the smooth shock wave, and it's where you can see the relative dominances of 0s and 1s are changing, as we saw in the previous coalescence, the previous pictures. So what we see is that actually at the smooth shock, and I'll show you this in a minute numerically to prove this, this isn't actually a caustic. It's not a caustic, because of course all the other, it should be a turning point because they've all coalesced there, but all of the infinite number of the green, the 1s, are all on mutually different Riemann sheets, and so there's no, they pass, if you look vertically below, if you look above the Borel plane, they would all be passing through each other, but they're all passing through on an infinite ladder below that, so there's no actual caustic. So this is actually a virtual turning point. This shock, this nonlinear shock position, turns out to be a virtual turning point, and that is then a higher order Stokes phenomenon that's caused that moving onto the different Riemann sheets. We can try and walk further on, but if you walk further on, things get a little bit more complicated, because well, first of all, you can't really sum these trans series here, because you've all got e to the 0s at that point, so it's not summable. So what the other issue that you've got is that, of course, you've now got anti-Stokes lines coming here, which leads to Stokes pole regions where you have to get past. However, in this case, you can do a resummation of the trans series. You can sum all these terms bit away from the virtual turning point, and you get this leading order behavior here. Because of this nice geometric progression here, you can get this expression. And when you actually then plot that expression, what do you get? Well, here it is. It's not too well, you can't really see it too well, but this is the smooth shock position here for t equals 5, epsilon equals 0.05. And then what I plotted from this point going up, this is going up and then going up down to here, is the trans series resummation. So the two things is, I've not plotted it beyond here because that's where the other caustic is. And there's also the other caustic here. You can see that this is a resummation trans series here, and it begins to diverge. But in the region of the smooth shock behavior, it doesn't diverge. It's perfectly beautifully replicating the smooth shock behavior, and gets that result there. So even though in theory you can't resum the trans series at that point, by analytic continuation here, it works. So that sort of gives you an analytical explanation of what's going on, and modulo these caustics at that point, you can get a good approximations as well. If you really want to see the gory result of what's going on here, this is for times less than where the caustics coalesce before the shock formation time. This is after the shock formation time. Here is our higher order Stokes line bubble here, and then what happens is you get these coalescences, and then these two active turning points, and then they move out here, the caustics. And what they leave is a ghost of a virtual turning point in the middle here, which then forms the position of the shock wave. So this is in the complex X plane here. And so that's essentially the shock position. And as it goes on, these bubbles basically go there. These dots here are the poles associated with the anti-Stokes lines here that you have to be careful of if you wanted to walk around. But in this particular case, you're lucky you've only got one line of them, you don't get an infinite number of them. And so you can walk off. Okay, so the conclusions of that to conclude is that the higher order Stokes phenomenon occurs generically. It can switch on the activity of Stokes lines, It's explainable in various ways. In this, one way of explaining it is looking at the Riemann sheet structure of the Borel plane. Things drop onto a different Riemann sheet and so can no longer cause Stokes phenomena. Another way of looking at it is there are algebraic cancellations in the higher and exact cancellations in the hyperasymptotic expansion of branches. It can affect large time behavior rolling forward, so it's important for PD time evolution problems. It can lead to virtual turning points, so where you think that things are blowing up, it actually turns out they end up as just shock points, which sometimes they don't blow up, but sometimes these have importance as they can be identified as nonlinear shock points. And one of the reasons I was asked to talk about this is whether this phenomenon has been explored in detail in Carl's research, so I would be very interested to know if it has and how it occurs in there. But thank you very much for listening. Apologies for overrunning slightly.
Thank you very much, Chris. So it is time for questions or comments. Yes, John?
You said you can get it in second order. It's not obvious to me you can't get it in first order if you put enough exponentials in the coefficients.
Sorry, in second order what? Sorry.
Oh, sorry, ODEs.
ODEs.
Yeah.
It may be possible. I've not thought about that, but it might, yeah.
I secondly had to step out of the room. The linear PDE, there's a bit where the asymptotics seem not to work. What was that?
Sorry, let me just go back there. Sorry, let me just come off here. Sorry, standard. Go all the way back here. Which bit?
About 2 slides later. No more.
Oh, that one.
Yeah.
Yeah. This bit here. I think this is a. I can't remember why. I think this is a caustic. I can't. I'd have to look back at the original code, but I think that was a caustic.
But we should be able to get that asymptotically, shouldn't we?
Well, if you do it
or
with matched asymptotics or something like that, you'd be able to do it. I mean, I've just done a simple endpoint. I've not attempted any uniform approximation in that region.
Okay, and finally, most importantly, you put W, K, B, and J in the wrong order.
That's a matter, yes.
Read Heading's book. He wrote it when he was at Southampton.
Okay.
Yeah.
All right. Yes. Yeah. I put the C in for you as well. It's
yes, thank you. Thank you.
Okay.
Yeah.
Okay. Yeah.
Who was the C?
Cassati, I believe.
Carlini or something, no?
Carlini.
Maybe.
Sorry, who's it?
Carlini.
Carlini.
Yeah.
Sorry, that's Carlini. Yeah,
Oh,
1817 or something. Yeah. Okay. Yeah.
Okay, I may have one question. So do you have interesting problems where you have to look at the later determinant functions, so F3, F4?
I don't have the will to, so I'm sure there may well be interesting ones there, but I've not gone that complicated.
Well, they should play a similar role to the higher order Stokes phenomenon, because an F3 can switch on an F2 and so on.
Yeah, Andrew's right. Yes, in principle, once you see it happens for 2 and 3, because of the form of the hyperdeterminants, they're always in terms of ratios. After the first level, they're always in terms of ratios of the singulants from where you're coming from and where you're going to in that particular next step. And so if you've that means that you can always have these higher order twigs, killing off lower order branches or cutting off other branches at lower orders as well. So yes, in principle, there will be functions that you can do this an infinite number of ways. You can have the nth order one switching off the n-1 and things like that. But I don't have examples of those.
There's one in the Bodie paper.
Oh, is there?
We go to
Oh,
third
okay.
order, yeah.
Okay, good. And that was what? That was a fifth order thing, was it?
Fifth order PDE. Yeah.
Fifth order PDE, yeah.
And do you have to then introduce kind of second, third, fourth order Stokes phenomenon, or from F2 onwards it's just a higher order Stokes phenomenon?
Well, we just called it the higher order Stokes phenomenon. I mean, yeah, I mean, in theory, you could have more than three coalescing, but then that gets more. You know, three coalescing in any direction is as common as two coalescing along one direction. But then three, if you had four coalescing along one direction, that would be rarer.
Mm-hmm.
Or sorry, not coalescing. I mean, being collinear. Sorry, that would be rarer. And I'm not talking there about the nonlinear case where you just get repetitions. I'm talking about the independent ones. But you know, I mean, the point is the nonlinear ones, they always move together.
Yep.
Whereas if you've got the independent ones, then they can move independently, obviously. So, yeah. But yeah, I mean, it would be interesting to know. I don't know Carl's work as well as I should do, and it would be interesting to know if it was in there. I mean, these are movable singularities, and it would be useful to know that. Okay.
Yes, so if there are no more questions, then we may stop recording and can have a more informal